Today I want to show you the tablecloth trick. It's a famous physics trick. In this demonstration we usually talk about inertia, but today I want to go a little bit further and also talk about impulse, or force times time. So I think it ties together well with several other demos we have. So the classic tablecloth trick starts with, you got to have a smooth table, a smooth tablecloth, and you want to have no seam on the tablecloth. We've taken the seam off of this one. That's just because when you pull the tablecloth out, if there's a seam, it can tend to pull this thing off. All right. So we all know what happens if you pull slowly on the tablecloth. Okay? The blocks go with it, there's friction, and the blocks are going to fall right off the table. But when you pull quickly on the tablecloth, correctly, you can actually have the blocks stay almost motionless. The key to doing this is to not lift the tablecloth. So if you lift the tablecloth and pull like this, a lot of times you'll end up flipping the blocks over. You'll lift up too much and flip the blocks. So what you want to do is pull straight down at the edge of the table. So it's almost as if this surface was a pulley. So when you pull down here on the tablecloth that's resting on the table will go straight this way. All right? And so when you do this quickly, you'll notice that the blocks don't move much, but they do move a little bit. And we typically say they have so much inertia, they're an object at rest, they tend to stay at rest. Okay? And so an object at rest tends to stay at rest is Newton's first law. But if you want to talk about how much they move, we need to discuss impulse or time. So in this case, what happens here is when you pull very slowly, the frictional force acts on these blocks for a long amount of time and causes it to move a certain distance. When you pull very quickly, the frictional force exerts, the friction between the tablecloth and the blocks will exert a force for a very small amount of time on the two blocks. And that means, since it's not exerting a force for a long time, it's not accelerating for a long time, so it doesn't get up much speed. And then when the tablecloth is removed, it's not going that fast, it doesn't take that much time for the table to slow it. And all that process ends up causing no significant motion of the block. So it does move, but it was accelerated for such a small amount of time. It takes almost no time to stop, and therefore it looks like it sits still. Okay. So now I thought we might do a close-up of this and zoom in and show you how the mass matters. An object with more inertia, so we could do this twice here, or we could do it with these two cups side by side. Oops, that's not a good way to do it. Let's go like this. People are always more impressed if you do this with something breakable, so that's a good recommendation. They also like it if you try making crazy shapes and stacking things, so that's another good thing to do. You can have them make the craziest thing and then see if they can jerk the tablecloth out quickly enough to not have it fall over. But in this case, what I thought we might do is look at these two beakers and try and line them up. So I've tried to set this one right at the 30 mark and this one right at the 10 mark. And then when I jerk this tablecloth out, we can see which one's going to move more. Now hopefully the one with larger mass, this one, it's got much more inertia, so it's going to tend to stay at rest more. They're going to have some friction acting on them. So let's see. The math is actually complicated, but we'll do that in class sometime. So here we go. 1, 2, 3. And you can see that this one has barely moved at all, maybe a few millimeters, and this one moved a significant distance. So the larger the mass, the easier this is. So if a kid's having trouble making this work, you have them use a bigger block, not a smaller block. So then it's more likely to sit in place. Oh, and there you go. That's the tablecloth trick.